Aloha BIOCHEM. In this video, we begin Chapter 2 and discuss atoms versus elements. Hello again. So we're starting Chapter 2, Atoms in the Periodic Table. In the picture you can see some helium-filled balloons. Helium is one of the elements, and it's a gas which is a little lighter than air, so when you fill a balloon, the balloons rise in air and sometimes they float away. Here's the chapter outline. Today we'll cover elements and compare elements and atoms. These are two important ideas, and sometimes the two are confused, so we'll make that clear today. And then for several sections and videos, we'll take a look inside the atom at the subatomic particles, and then at the end of the chapter, we'll discuss a few important periodic trends. So the chapter is titled Atoms in the Periodic Table. Now, atoms, these are the building blocks of matter, the tiniest particles of matter, or like the Legos of matter. When you were a kid, maybe you played with Legos, which are these tiny little pieces, and they could be assembled together to form larger objects and so on. And in a similar manner, all of the material that we see around us is made of tiny particles that can be assembled together to form different types of material. Now, although there are smaller subatomic particles, the atom is the smallest stable particle of matter. It's very difficult to cut an atom in half, and even if you could do it, you would basically end up with unstable pieces, and they would reassemble to form other atoms. So atoms are the smallest stable particles of matter, and they're also the smallest pieces of an element. So all matter is made of atoms, and so elemental matter is made of atoms. The difference between atoms and elements is as follows. An element is like a substance that you could put your hands on, you could feel it, like the element gold is a nice metal, and you could feel gold. It has its properties. Iron is a different element with different properties. Well, the gold is made of gold atoms, and the iron is made of iron atoms. And the reason gold is different than iron is because gold atoms are different than iron atoms. So you see, atoms are simply the tiniest particles of an element. And the reason we have different elements is because their atoms are different. So we've all seen the periodic table of elements, and what it really is an organized list of the different types of atoms that we know about. And it's also an organized list of the different types of elements, because for each element there is a corresponding atom. So let's take a quick look at the periodic table. This is my favorite one to look at right here. It has lots of information. It shows you which elements are the solids, the liquids, and then the gases, and also it shows you the metallic elements and the non-metallic elements. So lots of information on here. I like this one. And there are other periodic tables that people use, and sometimes there's even fun periodic tables, such as the periodic table of elephants, which each spot is an elephant. So we will get to know this table and why it's structured the way it is. So basically it lists all of the 118 elements that we know about. So it's starting at element 1, hydrogen, and continuing with element 2, helium, and element 3, lithium, and all the way up to element 118. So each one of these 118 elements has its own unique type of atom. And so for the 118 elements, there are 118 different types of atoms. And in this chapter, we learn about what makes one atom of one particular element different than an atom of another particular element. So why are carbon atoms different than oxygen atoms? Well, when we go through this chapter, we'll answer that question, and that'll tell us why carbon is different than oxygen. Let's recall what elements are. The definition of an element is it's a substance that cannot be broken down into simpler substances by any physical or chemical means. So it's a substance that no matter what you do to it, you can't divide it into any simpler substances by any physical or a chemical reaction. So it's a simple substance itself. If you recall, in the previous chapter, we discussed the process of simplifying different substances, and let's recall that. So if you start with, say, some salt water, this is a mixture of salt and water, and it's easy to separate into its salt and water substances by the process of distillation. You boil off the water, and then the salt is left behind. And so you can pretty simply separate salt water. Now, salt and water are both compound substances, meaning they are pure substances themselves. Water is water no matter where it comes from. If you have water and it's pure, it looks just like any other pure water that you come across. Okay? So unlike salt water, you could have some really salty water in one place, and then other salt water would be not so salty. So the proportions of salt to water can vary, and that's what makes this a mixture. But when you get to a compound substance, it's the same no matter where it comes from. But it's a compound substance because it can still be broken down into its constituent elements. And water can, in fact, be broken down into hydrogen and oxygen through the process of electrolysis. So salt as well can also be divided into its constituent elements, sodium and chlorine. Now, if you take another mixture like air, air is a mixture of many different substances. Some of them are elements, in fact. Air is composed primarily of nitrogen, but there is also some oxygen in there and a tiny amount of argon, another element. But there, depending on where you are, you might have some carbon dioxide in the air, which isn't an element, it's a compound, but carbon dioxide can be broken down into its elements. And so eventually even air, any chunk of material can be eventually broken down into its elements. Now, if you take a third example, like table sugar, such as can be extracted from sugarcane or beets. So if you get a hold of some table sugar, this is already a pure substance. And although it's difficult to do, you can break down sugar into carbon, hydrogen, and oxygen. Now notice that when you break down material into its constituent elements eventually, you see a lot of repeats. So, you see hydrogen over here from the salt water that came from the water, and then you see hydrogen over there from sugar. And sugar also has oxygen, and air has oxygen in a couple places, from the oxygen component and also from the carbon dioxide component. And then salt water has oxygen from the water component. And so you see a lot of repeats. Notice that there are more than 4 elements. Okay, right here, just from these 3 chunks of material, we saw 1, 2, 3, 4, 5, 6, 7 different elements. So there's more than 4 elements, unlike the Greeks thought there were. So the Greeks had this theory that all matter is made of 4 elements: earth, water, air, and fire, and they thought that all substances out there could eventually be broken back down into those 4 elements. But through the ages, we have learned that there are many more than 4 elements. So I'm sorry, Aristotle and Empedocles, that theory of 4 elements isn't quite correct. Now, just like their theory wasn't quite correct, the first atomic theory wasn't quite correct either. And back in Aristotle's day, there was this philosopher named Democritus who first, discussed the theory of atoms. Actually, he wasn't the first one, but he popularized the concept of atoms. And he thought that the reason there's all this different types of material like water and salt and etc. is because water is made of water atoms and salt is made of salt atoms. But the mistake that he made was he thought that every different type of material had its own unique type of atom. And so that meant there were like millions of different types of atoms. And we know that that's not the case either today. We know today that there's 118 different types of atoms. Okay, there's not an unlimited number of different types of atoms like Democritus thought. And Aristotle actually had a problem with Democritus's theory for that very reason. Aristotle didn't like the idea of an unlimited number of different types of things. And he didn't like the idea that stuff was made of tiny particles either. He thought that you could keep on cutting matter in half and cutting matter in half, and you would never get to a smallest particle. Aristotle thought that matter was continuous. Democritus thought that it was corpuscular or particulate. So two competing theories. Democritus's theory went by the wayside, and the theory of the four elements continued on for a couple thousand years, but then eventually there was a reckoning, and they both kind of went by the wayside, and we still hold on to pieces of both of their theories today, but we know a lot more information today, so you can't blame them. Show you a quick picture of Aristotle and Democritus. So here's Aristotle. Matter is continuous, four elements of matter, and here's Democritus. Matter is particulate, and there's millions of different types of atoms. So we do know about the various elements today. There are 118 elements as listed and organized on the periodic table. And the way they are arranged is mostly in order of increasing atomic mass. Let's take a look at the periodic table. I'll show you another one that's in your textbook. Okay. Actually, before I show this to you, let me show you first the element symbols. And here you see each element has its own symbol. So this is table 2.1 and 2.2 in your text, and you see, bromine element is represented by the letters BR, and cobalt by the letters CO, capital and then lowercase. And some elements only have one letter, like fluorine and carbon. And some elements are named after their Latin names and German names, like antimony, symbol is SB for stibium, and sodium comes after the Latin natrium, so sodium is Na, and potassium is K. Okay, so each element does have a symbol. So when you see periodic tables, a lot of times you'll just see the symbol. So here's figure 2.1 in your textbook, which is the periodic table of elements. It shows all 118 of them. And notice that these elements are listed in order of how heavy their atoms are. So the 118 elements all have their own unique type of atom, and these atoms all have a certain mass. Okay? Now the lightest atom happens to be the first element in the table. Hydrogen atoms all weigh 1.008 atomic mass units. Okay? An atomic mass unit is very small. It's much smaller than a microgram or a nanogram. So this number down here tells you how heavy hydrogen atoms are. They're 1.008 atomic mass units. And going over to element number 2, helium. Helium atoms weigh 4.003 atomic mass units. And going down to the next row, element number 3 is lithium. Lithium atoms weigh 6.941 atomic mass units. And you'll see the atomic mass increase as you go further along the list. So chlorine is 35.45 atomic mass units per atom, and argon is 39.95 atomic mass units per atom. And they get heavier and heavier and heavier. But there are a couple of discrepancies. Notably, when you go from element 52 tellurium to 53 iodine, you see the atomic mass actually decreases a little bit. So why is that? There are maybe a few other exceptions to the atomic mass rule, and it turns out that the reason iodine doesn't come before tellurium is what this chapter is all about. You see, in this chapter, we take a look inside the atom, and once we do that, we'll see why the periodic table is arranged the way it is, why it has this interesting shape, and why there are even small discrepancies in the ordering of the elements by atomic mass. Okay, you might be able to find a couple of other discrepancies if you look. So there are lots of elements in the table, and rather than just thinking about the 118 elements, we like to categorize things. You know, we like to organize things in science into different categories. You have these types of elements and those types and those types. And so people have thought about this a lot, and there are different ways to categorize the 118 elements. And the main way to do that is by metals and nonmetals and metalloids. So the metals you'll mostly find on the left-hand side of the periodic table. These are the green ones. So if you look again, you see these green ones. These are the metals. And the nonmetals are the blue ones on the right. And then the metalloids are these orange ones in the middle. Okay, hydrogen is a nonmetal, but it's on the left with the metals, and there's a good reason for that, but that's for the most part. So you can divide elements into those three categories. Metals are shiny substances. They conduct heat and electricity very well. They're ductile, and that means they can be drawn into a metal wire. And they're malleable, so if you have like a plate, you can hammer it into different shapes. And metals are also, for the most part, solid. Now, nonmetals, on the other hand, which are on the right side of the periodic table, you'll find them in all three phases, mostly gas. They are not shiny substances like the metals are, and they do not conduct heat or electricity very well, and they're not ductile and malleable. In fact, if you do have a solid element like sulfur, solid sulfur, and you try to hammer that, that'll just chisel away. It's very brittle. It's not ductile or malleable. So they're very different than the metals. And then the metalloids, which occupy that region between this region between the metals and the nonmetals, they have properties intermediate. And if you look at, say, the metalloid silicon, it doesn't quite conduct electricity as well as the metals, but it's not so much an insulator like the nonmetals, and it's a semiconductor. And so silicon is used in electronic circuitry where semiconductors are needed. So that's one way to categorize the elements, metals, nonmetals, and metalloids. But there are other ways to do it. We could ask which ones are the solids, which ones are liquids, and which ones are gases. And it turns out that there are 2 liquid elements under normal, conditions. Of course, you can melt elements into their liquid state, but under normal conditions, only 2 of them occur in the liquid state. Maybe you can find out which 2 they are. Okay, so that's another way to do it. And a third way to categorize them is by what type of particle they're composed of. So if you have an element and you look at the tiny particles that make it up, are they single atoms? If so, it would be an atomic element. But sometimes for some elements, the particles are not single atoms. The atoms like to latch on together to form molecules, like the element oxygen. Oxygen is made of oxygen molecules, where two oxygen atoms are always latched together. And you never find any oxygen where it's single oxygen atoms, or if you do, it's unstable, and that single oxygen atom is looking for a second one to latch onto. So oxygen comes in the form of two atom molecules. So some elements are molecular, and there is a third strange category called covalent network. This is a third way to categorize the elements by what type of particle they're composed of, and there are other ways to organize the elements into different categories. Now, in the previous chapter, we did discuss elements and compounds. So an element is a substance that cannot be broken down any further. It's a simple substance, but compounds can be broken down further into their elements, in fact. So you either have a substance is either elemental or it's a compound substance. Now, elemental substances are much fewer in number. There are only 118 that we know about, but there are many more compounds, possibly an infinite number of compounds. No one really knows. And for that reason, elements are more rare than compounds because there are much less of them. You're much more likely to come across a compound out there in nature. But even compounds are kind of rare. Most matter that you come across is a mixture of many different substances. And just as there are various ways to categorize the elements, there are also different ways to categorize the compounds. And in chapters 3 and 4, we'll talk about the two main categories of compounds. So compounds are like when elements combine together to form a substance. So we say that elements chemically combine in fixed proportions to form compounds. So we talked about what this means in the previous chapter. So if you remember, like the compound substance water, there are always 2 atoms of hydrogen for every 1 atom of oxygen. So the proportions of hydrogen atoms to oxygen atoms is always fixed. And that's why we represent water as H2O. So every substance, whether it's an element or whether it's a compound, has a chemical formula that you can represent it as. So elements are much easier to represent because there's only one element symbol in there. So, here's a few examples of elemental substances and, the chemical formulas that represent them. So sodium, solid sodium, notice that you have the element symbol and then the state that it's in. Solid gold. So the symbol for gold is AU. And the way I remembered that was AU, give me back my gold. So solid gold. Solid iron, Fe for iron, that's ferrum, after the Latin for iron. And then, liquid mercury, gaseous argon. Now, some elemental substances come as molecular particles. So these elements over here, their tiny particles are made of just single atoms. And the ones over here, they are composed of molecules. So oxygen, we already mentioned, comes in the form of O2 molecules. So gaseous oxygen. So if you have some oxygen gas, and you look at the smallest particles, you'll see 2 oxygen atoms latched together as a molecule. Hydrogen also does that. Nitrogen does that. And phosphorus, you find even 4 atoms of phosphorus per molecule, and you'll find 8 atoms of sulfur per molecule. So I'll show you an interesting a picture of this, these molecular elements. So here's a picture of some of these molecular elements. So hydrogen, this is what a hydrogen molecule kind of looks like. Here's the space filling model. The atoms sort of overlap with one another, and here's the ball and stick model, which is sometimes useful. Nitrogen does that too. So nitrogen is a diatomic element, so 2 atoms per molecule, a molecular element. Oxygen is also 2 atoms per molecule, so O2. Fluorine does that, chlorine does that, and bromine and iodine. Okay, now phosphorus, which comes in the form of P4 molecules, which are tetrahedrally attached. Here's the space filling model, has an interesting shape. Sulfur, the 8 sulfur atoms actually attach together in a ring. So a very cool structure for a sulfur molecule. Now sulfur is a solid substance, and you can find that at the base of volcanoes. So perhaps the volcano on the Big Island, if you walk around after the lava cools, you can find some yellowy solid substance, and it might even look crystalline, and that would be sulfur crystal. And so you can compare the chemical formulas for elements with those of compounds. Now, of course, compounds have more complicated formulas because they have different types of atoms in the chemical formula. So water, for instance, is H2O, liquid. Water normally comes in the liquid phase. But there is a different compound substance that's made from hydrogen and oxygen, and that's hydrogen peroxide, H2O2. So you see, a molecule of hydrogen peroxide has 2 hydrogens inside there and 2 oxygens, whereas a molecule of water only has 2 hydrogens and 1 oxygen. Formaldehyde is CH2O. That's a liquid. It's used in embalming bodies, preserving them. C6H12O6, that's the formula for glucose, sugar. So glucose molecules are quite a bit bigger than the other ones we saw. There are many atoms inside here, and the structure of the molecule is kind of interesting. We'll take a look at a glucose molecule later on. Sometimes in the chemical formula you see the atoms are separated, instead of all grouped together like 6 carbons. Down here in the following formula you see a carbon here and a carbon over there. Then you see hydrogens in 3 different places. The reason that's done is because you're being clued in as to what the molecule looks like. In other words, how the atoms are attached. These 3 hydrogens are attached to that carbon atom. Those 2 are attached to the second one. And then that hydrogen is attached to the oxygen. And somehow they all connect together. So this is the formula for liquid ethanol. Now in your textbook, the molecules can be drawn as ball and stick models, as we just saw. So let me show you a few examples. So here, the different atoms are color-coded. Carbon atoms are black, hydrogens are white, and so on and so forth. And if you remember this color coding scheme, especially the first 4, those are the most important elements in biochemistry. If you remember that color coding scheme, then you can look at ball and stick models of various substances to see what they are. So looking at this first one right here, you have 1 black atom connected to 4 white ones. So the black one, again, is carbon, and the white one is hydrogen. So the chemical formula for this would be CH4. That's methane. Now look at the next one. The blue one is nitrogen. So this is NH4. CH3, or ammonia. And then this one right here, this is ethanol. So we already saw ethanol right down there, CH3CH2OH. Here's your CH3, CH2OH. And so that's what a molecule of ethanol looks like. And that's why the formula is written like that. And you can find more complicated examples, and your textbook does have a few of those. Here's the model for caffeine molecule. And so you can count up all the carbons. You got 1, 2, 3, 4, 5, 6, 7, 8 carbons. So it would be C8. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C8H10. And then nitrogens, you got 4 nitrogens. C8H10N4. And then O2. So that would be the formula for caffeine. So these compound substances right here are actually a different category than those over there. Just like there are various ways to categorize the elements, there are various ways to categorize the compounds. And in chapters 3 and 4, we'll discuss covalent compounds and ionic compounds. Ionic compounds, you'll almost always see a metal in there. So like sodium chloride, solid. Iron, this is called iron 3 oxide, solid. This is actually rust. Magnesium hydroxide, solid. This is the substance you find in milk of magnesia. Zinc nitrate. Gold chloride, gold 3 chloride actually is the name. So these are ionic substances and these are covalent substances, and we'll talk about those later. Now, to finish off this lecture today, let's discuss the elements of life. So which elements make up the human body? And your author has a nice diagram of this. So here are the elements of life. In other words, the elements that make up the human body. You should know of the 4 building block elements that comprise 96% of the mass of the human body: carbon, oxygen, hydrogen, and nitrogen. The major minerals compose, most of the remaining 4%. There are 7 major minerals: potassium, sodium, and chlorine you'll find present in body fluids. Magnesium and sulfur are present in proteins found in the muscle. Calcium and phosphorus are found in teeth and bones. You need at least 100 milligrams of these, each of these 7 major minerals in your daily diet. Now, the remaining tiny percent of the human body is composed of trace elements. So here are a lot of trace elements: argon, arsenic, boron, etc. And these have different roles in biochemistry, and you need a much smaller quantity, 15 milligrams or less of each of these in your daily diet. So as long as you have a well-balanced diet, then you get everything that you need. I like to look at the breakdown of elements in the human body a little bit differently. So here's another picture which might help you see it a little bit more clearly. So, here's your human body, and here are the 4 building block elements that make up 96% of the human body. Most of it is oxygen. You see, oxygen's at the top at 65%. The next comes carbon, 18% about, and then hydrogen, and then nitrogen, and then the other major minerals and trace elements occupy that remaining 4%. Okay, so here are the 7 major minerals as they are listed according, in decreasing quantities by mass, percentage mass in the human body, and then the trace elements are, less than 1% of the human body are trace elements. And one more breakdown of the substances found in the human body is actually by substance, not by element. So the reason most of the human body is made of oxygen is because most of the human body is made of water, and water is mostly oxygen. Okay, a lot of the human body is made of protein tissue, 20% of it, and proteins are made mostly of carbon, hydrogen, nitrogen, and oxygen. Okay, fats are mostly carbon and hydrogen, and the body is about 10% fat. And there are 4% minerals and 1% carbohydrates. So this picture shows you how the human body is divided into different types of substances. So anyway, that concludes this lecture. In our next lecture, we will discuss the atomic structure. So we're going to take a look inside the atom and see what makes atoms of one element different than atoms of another, and therefore that's what makes the two elements different from each other. So coming next, stay tuned.